Hi, Keith here, and in this video I'm going to look at why you should always use the most complete model you can when analysing your data, and I'll highlight some of the problems that can occur if you don't. And this video I'm looking at this from the perspective of standard analysis of variance. So here I've got some data. Doesn't matter what they are, and I invented them specifically for this particular video. There is factor A and factor B, and if I scroll you can see they both have just two levels. Now what I have seen some people do when they think that things are a bit too complicated is to analyse for factor A ignoring factor B because it's a nuisance factor, or perhaps the other way around. Now, let's look. So here is the one-way ANOVA using just factor A. Note, the p-value is 0.142, so this is not significant, and the confidence intervals overlap considerably. So clearly there's no effect of factor A here. And note, the mean square for factor A is 1923 and the total sum of squares is 16620. This is the actual means for factor A looked at as box plot, giving you pretty much the same idea that you would from the analysis of variance itself. If there is any difference, A1 is going to be smaller than A2. Let's go to factor B and we get a similar outcome, although the p-value is 0.09, so it's getting down there a bit. The confidence intervals still overlap considerably. And I've lost the box plot. There we are. Same story for factor B. B1, if anything, is going to be smaller than B2. Looking at the averages. Okay. Let's go and do it properly. I'll use general linear model for a reason I'll come to in a moment. And I've got to do the interaction plot for the AB interaction. So here we go, we'll come back to that. Here's the analysis. F values for all three sources are very large and the p-values are very small, all less than 0.001. So there is an effective factor A and B and a very large interactive effect, none of which was evident in the individual analyses. And we can see why. Up here you'll see the adjusted mean square for factor A is 1923, which if you remember, and I'll go back there, is the same as we saw for the one factor. Total is 16620, again the same as the one factor. Look at the error here. 95 for sums of squares, 6 for mean square. Back here, 1923, as we just saw, that's the same number as in the two-factor. 16620, the same number as in the two-factor. The big difference here is the error. The error here is now nearly 15,000 with a mean square of 1816 rather than 6. What happened is everything that is, variation that is not explicitly identified ends up in the error. So the error term there is a total of the variation for factor B and the interaction. If we go and look at factor B and its analysis, the same story. 16620, same total sums of squares, 2484. When we go back to the two factor, we'll see that's the same number. But here, the error term, 14,000, with a mean square of 785. That's because the error is error plus factor A variation plus A times B variation. 2484, 2484. And there's the variation for the interaction. It's very large, 12,000. In fact, it's far and away the largest source of variation in this particular analysis. So, running analyses on factors, ignoring other elements of variation, can give very misleading results. Now, I haven't put a covariate in this design or in this analysis, but the same thing can happen with it if there is a covariate that has been measured and it's not included in the model. Now, we got the interaction plot, so let's look a bit more. Well, that's a very different picture from what we got from looking at the marginal means. Average for B1 and B2, and the average for A1 and A2. If we just go back to those, let's see. A1 less than A2, B1 less than B2. Oh no. It very much depends what combination of factors we're looking at. For A1, B1 is larger by a good bit than B2. For A2, it's the other way around. And if we plot the interaction plot the same way, plot the interaction plot the other way around, and what I mean is by doing like this. Now we're looking at level B. For B1, A1 again is larger than A2, but for B2, A1 is less than A2. Very similar pattern for both factors here because that's the way I set the data up. But the marginal means, all A1 versus all A2, and all B1 versus all B2 give very misleading ideas about what's going on because there is a very large interactive effect in the set of data. That's all.